A truly remarkable visitor from the depths of space, Comet 3I Atlas holds secrets from before our solar system was born. If you enjoy these calming facts to help you relax and sleep, a gentle click on the subscribe button ensures you'll never miss another journey. The first hint of this comet's existence was not a grand vision in a telescope, but a faint and unassuming smudge of light on a digital sensor. It was detected by the Asteroid Terrestrial Impact Last Alert System, a robotic survey network known as ATLAS with telescopes in Hawaii. This system isn't designed to leisurely gaze at the cosmos. Its primary mission is a frantic one: to scan the entire observable sky every few nights, searching for moving objects that could pose a threat to Earth. Its powerful cameras and software are built for speed and efficiency, sifting through millions of stars to find the one tiny point of light that isn't where it's supposed to be. It was in this automated, vigilant sweep of the heavens that the comet first betrayed its presence, a silent traveler caught in a digital net cast across the darkness. Its epic journey from the outer void suddenly given a name and a destination in our awareness. This momentous discovery occurred on December 28, 2019. As the world prepared for the end of a decade, the Atlas telescope on Mauna Loa captured the series of images that held the comet's faint signature. For the astronomers who verified the finding, it was a quiet, profound moment. A new member of the solar system had been cataloged, designated C/2019 Y4 Atlas. The name itself is a story. The C indicates it is a long-period comet, not one trapped in a regular, repeating orbit. 2019 marks the year of its discovery, and Y4 is a celestial code, meaning it was the fourth comet discovered in the second half of December. It was a methodical, almost bureaucratic naming for an object that would soon ignite the imaginations of millions, a cosmic ghost that had finally materialized in our instruments after an unimaginably long voyage through the cold. When first spotted, Comet Atlas was profoundly faint, a mere whisper of an object lurking in the constellation Ursa Major. It registered at a magnitude of 19.6, a number that signifies an incredible dimness, far beyond the reach of human eyes or even a large amateur telescope. To put this into perspective, the faintest stars we can see from a dark, clear sky are around magnitude 6. The magnitude scale is logarithmic, meaning this comet was hundreds of thousands of times fainter than the dimmest naked-eye star. It was a ghost in the machine, a potentiality that required immense technological power to even perceive. Its light had traveled for years to reach the telescope, carrying the first clues of a story that began in the deepest, most frozen expanses of our solar system, a story that was only just beginning to unfold for its new audience on Earth. Every piece of information about a new comet is a puzzle piece, and its name is the first one placed on the board. The official designation, C/2019 Y4 Atlas, is a concise astronomical biography. The leading C immediately told astronomers this was not a familiar, returning friend like Halley's Comet. This was likely a non-periodic comet, meaning its journey into the inner solar system was a one-time event on human timescales. Its orbital path so vast that it might not return for thousands or even millions of years, if ever. The 2019 is its birth year in our catalogs. The Y represents the 24th letter of the alphabet, corresponding to the 24th half-month of the year, which is the latter half of December. And the 4 signifies it was the fourth such object found in that 2-week period. The final part, Atlas, honors the robotic survey that found it, forever linking the comet to its automated discoverer. Initial observations quickly allowed astronomers to trace the comet's path back through space and project its future trajectory. The calculations revealed a nearly parabolic orbit, a specific type of elongated, open-ended curve. This was a critical clue to its origins. Such an orbit strongly suggested that Comet Atlas was a first-time visitor from the Oort cloud, a theoretical, immense sphere of icy debris thought to encircle our solar system at a distance of up to a light-year away. This meant the comet was not just a rock, but a pristine relic, a frozen time capsule from the very formation of the planets, 4.6 billion years ago. It had spent eons in a deep freeze, undisturbed, before some distant gravitational nudge sent it on its long, slow fall towards our sun, bringing with it the ancient chemical ingredients of our own world. As astronomers watched, something extraordinary began to happen. The faint smudge started to brighten, and it did so at a remarkable rate, far faster than expected for a typical comet. By March of 2020, its brightness was increasing so dramatically that projections began to circulate throughout the astronomy community, sparking immense excitement. The calculations suggested that as it made its closest approach to the Sun in May, Comet Atlas could become spectacularly bright, potentially reaching a magnitude of +2, or even rivaling the planet Venus in the twilight sky. It was heralded as the potential Great Comet of 2020, a once-in-a-generation celestial event that could be easily visible to the naked eye across the Northern Hemisphere. The world, locked down and looking for hope, turned its gaze upward, anticipating a breathtaking spectacle from this mysterious visitor. Through powerful telescopes, another beautiful and surprising characteristic emerged. The comet developed a vast glowing atmosphere, or coma, which exhibited a distinct and ethereal green hue. This striking color is a common but always captivating feature of comets, and it's not from the ice itself, but from the chemistry being unleashed by the sun. As solar radiation, particularly ultraviolet light, bombards the simple molecules sublimating from the nucleus, it breaks them apart. In the near vacuum of space, molecules like diatomic carbon, C2, and cyanogen, Cn, are created. When these specific molecules are energized by the sunlight, they fluoresce, emitting light in a very specific, ghostly green wavelength. This meant that the comet wasn't just a point of light, it was painting the vacuum of space with its own unique, glowing atmosphere, a sign of its ancient chemistry awakening under the sun's warm gaze. The scale of this awakening was almost beyond comprehension. While the solid nucleus of Comet Atlas, the icy core hidden within the glow, was estimated to be just a few kilometers across, its gaseous coma swelled to truly astronomical proportions. By mid-March, long before its peak brightness, the diameter of its fuzzy green atmosphere had grown to an estimated 720,000 kilometers. This is a staggering size, roughly half the diameter of the Sun itself, and substantially larger than the diameter of the planet Jupiter, the largest planet in our solar system. It's a profound illustration of how a tiny, solid object, when activated by solar energy, can generate an atmospheric structure that dwarfs entire worlds. The comet was a tiny heart with an immense, ethereal body, a testament to the power locked away within these small, icy wanderers. As researchers refined their understanding of the comet's vast orbit, they uncovered a fascinating historical echo. The path of Comet Atlas through the solar system was almost identical to the trajectory of another brilliant comet, known as the Great Comet of 1844. The orbits were so similar that it was highly improbable to be a coincidence. This led to a compelling theory. Comet Atlas and the 1844 comet were not siblings, but fragments of the same, much larger parent body. The idea is that a giant progenitor comet, perhaps hundreds of kilometers wide, ventured too close to the Sun many thousands of years ago and was shattered by the intense heat and gravitational forces. We weren't just witnessing a single comet, we were seeing a ghost, a piece of a much grander object whose other fragments had passed this way before and may pass again in the distant future. The journey of this celestial fragment was one of incredible velocity. Having fallen from the gravitational edge of the solar system for millions of years, Comet Atlas was moving at a breathtaking speed as it neared the Sun. In the early months of 2020, its velocity relative to the Sun was increasing daily, eventually reaching speeds of over 100,000 miles per hour. This wasn't a gentle drift, but a silent cosmic plunge. Each day it covered millions of miles, an inexorable and unalterable path dictated by gravity. This immense speed is why comets from the Oort cloud are so transient in our skies. They do not linger. They arrive with incredible momentum, swing violently around the Sun, and are then flung back out into the darkness from which they came. Their brief, fiery moment of glory, a fleeting spectacle in the grand, slow dance of the cosmos. The most definitive proof of the interstellar origin of Comet 3I/Atlas lay in a single, powerful concept: its hyperbolic excess velocity. This isn't simply a measure of speed, but a measure of unbound energy. Imagine tossing a ball into the air. No matter how hard you throw it, Earth's gravity will eventually pull it back down. However, if you could somehow throw it faster than escape velocity, it would leave Earth forever. In the same way, any object born within our solar system, even from the distant Oort cloud, is gravitationally bound to the Sun. Its path is a vast, closed ellipse. But 3I Atlas was moving so fast, even far from the Sun, that our star's gravity was fundamentally incapable of capturing it into an orbit. Its trajectory was a perfect hyperbola, an open-ended curve. This high excess speed is the telltale signature of an object that has fallen into our solar system from the vast gulf between the stars, a traveler merely passing through, destined to never return. To be certain it wasn't a native of our system, astronomers had to rule out the Oort cloud, the most remote region of the solar system. Comets from this icy sphere can have orbits that last millions of years and stretch incredibly far, but they are still technically closed ellipses. They are members of our solar family, just living on the very edge of the property. The mathematics that describe their paths, while showing extreme elongation, ultimately predict a return. The trajectory of 3I/Atlas was fundamentally different. Its path wasn't an ellipse, no matter how stretched. It was a hyperbola. The distinction is absolute. An ellipse is a path of an object that is captured. A hyperbola is the path of an object that is just visiting. By calculating its orbital eccentricity, a number that defines the shape of an orbit, scientists found it was significantly greater than 1, the mathematical dividing line between a bound object and an unbound one. It was a clear, unambiguous sign that the comet was not one of ours. Further evidence came from the comet's inclination, the angle of its path relative to the flat plane where all the planets orbit. Most objects in our solar system circle the Sun on or near this flat disk, known as the ecliptic plane, because they all formed from the same spinning cloud of gas and dust. But interstellar visitors don't share this history. They can arrive from any direction. Comet 3I Atlas plunged into our system at a steep angle of about 134 degrees. An inclination of 90 degrees would mean coming in straight down from the top of the solar system. An angle greater than 90 degrees, like that of 3I Atlas, reveals something even more unusual. It means the comet was not just coming from an odd angle, but was also traveling in the opposite direction to the planets. This kind of trajectory is exceedingly rare for native objects and is a powerful indicator of an external origin. This backward journey is known as a retrograde orbit. If you were to look down upon our solar system from above the Sun's north pole, you would see all the planets orbiting in a counterclockwise direction. This shared motion is a relic of the angular momentum from the primordial solar nebula. An object in a retrograde orbit, however, moves clockwise against the general flow of cosmic traffic. This is what 3I/Atlas was doing. For a native object to achieve such an orbit, it would require a massive gravitational disturbance, like a near collision with a giant planet. But for an interstellar object, which never shared our system's formative spin, coming in from any direction is perfectly normal. Its retrograde path was not the result of a chaotic event within our system. It was simply the path it was already on as it drifted through the galaxy, a path that happened to be oriented opposite to our own. To truly confirm its origin, astronomers performed a kind of celestial forensics, tracing the comet's trajectory backward in time. They calculated its path before it was significantly bent by the sun's gravity, projecting it back for millions of years. This revealed its incoming asymptote, the straight-line path it followed through interstellar space long before it ever felt our star's pull. For a comet from the Oort cloud, this line would trace back to the outer edges of our own solar system. But for 3I Atlas, the line pointed unequivocally toward deep space, toward a point far outside the sun's gravitational kingdom. It's a strange and calming thought, isn't it? To imagine these silent travelers on journeys that last for eons, their paths only briefly intersecting with our own. What do you find most comforting to think about when you're trying to fall asleep? The calculation was made even more complex by the comet's own activity. As 3I Atlas neared the sun, the ice on its surface began to vaporize, creating jets of gas and dust. These jets don't fire evenly. They erupt from random spots, acting like tiny, unpredictable rocket thrusters that gently push the comet off its purely gravitational path. These are called non-gravitational forces, and they must be carefully accounted for. Scientists had to model the effects of this outgassing and subtract them from the comet's observed motion. It was only after they had corrected for the comet's own self-propulsion that they could be sure about its underlying trajectory. The result was clear. Even after accounting for the push from its own jets, the comet's path was still strongly hyperbolic. The confirmation was a masterpiece of precise celestial mechanics, proving its interstellar nature beyond any reasonable doubt. Once its path was traced backward, the next logical question was, which star did it come from? But for 3I Atlas, as with the other interstellar visitors, its stellar home remains a complete mystery. The reason for this lies in the immense timescales of its journey. It likely spent millions or even tens of millions of years traveling through interstellar space. During that vast expanse of time, our galaxy has been in constant motion. Stars, including our Sun and the comet's parent star, have orbited the galactic center multiple times, drifting and shifting their positions relative to one another. By the time the comet arrived here, its home star had moved to an entirely different part of the galaxy. Tracing the path back leads only to an empty patch of space, the former location of a star that is now long gone, its identity lost to the slow, inexorable dance of the Milky Way. Its journey provides a fascinating point of comparison with the two interstellar objects discovered before it. The first, Oumuamua, was a strange, rocky object on a highly hyperbolic path. The second, 2I Borisov, looked and behaved much like a typical solar system comet, just with an interstellar trajectory. 3I Atlas seemed to fit the mold of Borisov, another icy body ejected from a distant star system. Each of these three visitors entered our solar system from a completely different direction and at a different speed, reinforcing the idea that our galaxy is filled with these wandering objects. They are not part of a single stream, but are more like cosmic driftwood, traveling on random paths, each telling a silent story of the planetary system it was born in. The discovery of a third object confirmed that these visitors are not impossibly rare, but a normal, if seldom seen, feature of our galaxy. While its parent star is unknown, astronomers could determine the direction in the sky from which Comet 3I Atlas appeared to arrive. As it coasted in from the interstellar void, its point of origin from our earthly perspective was in the direction of the constellation Hercules. This mighty celestial hero, one of the largest and oldest recognized constellations, became the backdrop for the comet's grand entrance. Of course, the comet did not originate from any of the stars within Hercules. They are themselves many light years away and unrelated. Rather, that patch of sky was simply the direction it was traveling from as it crossed into our cosmic territory. It's a poetic thought, this icy messenger emerging from the star fields of the celestial strongman, carrying with it the secrets of a solar system we will never see. Just as it had a point of entry, the comet has a mapped-out departure. After its brief, sweeping encounter with our Sun, the star's gravity acted like a slingshot, bending its path and flinging it back out into the galaxy on a new heading. Its exit trajectory is aimed towards the constellation Leo, the Lion. For centuries to come, long after it has faded from our most powerful telescopes, 3I Atlas will be silently sailing away from us, heading towards that new quadrant of the night sky. Its visit was a fleeting moment, a complete story with a beginning, a middle, and an end, written in the language of gravity. It arrived from Hercules, swung past our Sun, and is now leaving forever towards Leo, a temporary guest resuming its endless, lonely journey through the dark. While the trajectory of such a visitor is a profound piece of the puzzle, the name we give it tells a story all its own, starting with the most important letter. The official designation for a future object like this, something we might call 3I/Atlas, would contain the letter I, a deceptively simple character that carries immense scientific weight. This I stands for interstellar, and it represents an entirely new category of celestial object, formally recognized by the International Astronomical Union. Before the arrival of Oumuamua in 2017, there was no need for such a designation. All known comets were labeled with a C, and asteroids with an A, because every object we had ever tracked was a member of our own solar system, bound by our Sun's gravity. The creation of the I category was a historic moment in astronomy, a quiet admission that our cosmic neighborhood has a door to the vast galaxy beyond, and that visitors can and do pass through it. This single letter officially separates these travelers from everything else we've ever known, marking them as true aliens to our home system. Following that crucial letter, the number in a name like 3I is elegantly straightforward. It is a simple, sequential count of confirmed interstellar visitors. The first object, Oumuamua, was officially designated 1I/Oumuamua. The second, discovered by Gennady Borisov, became 2I/Borisov. Therefore, the designation 3I is reserved for the very next object that scientists can prove beyond any doubt has journeyed from another star system. This number isn't a measure of size, brightness, or composition. It is purely a chronological marker, like pages in a guest book for the solar system. Each new entry is a monumental event, adding another precious data point to our understanding of what the universe is like outside our own familiar bubble. The wait for 3I is a quiet, patient vigil kept by astronomers worldwide, knowing that the next knock on the door could come at any time, from any direction, adding the third chapter to this extraordinary new story of interstellar exchange. And so, the hypothetical name 3I Atlas signifies not a past discovery, but a future hope, the confirmation of the third ever interstellar object found by a specific observatory. The discovery of a 3I would be profoundly significant. Finding one visitor could be a fluke. Finding two suggests a pattern. But finding a third would begin to transform our understanding from novelty to statistics. It would help scientists calculate just how common these wandering objects are. Are there millions of them silently drifting through the galaxy for every star, as some models predict? The confirmation of 3I would lend heavy support to such theories, implying that the building blocks of planets are regularly ejected from their home systems and cast out into the void. It would mean that the galaxy is constantly swapping materials between star systems, a slow but vast process of cosmic sharing that could have implications for how life itself might sprout across the cosmos. Every new interstellar detection makes the universe feel a little more connected. This unique numbering and lettering system was established precisely because our old methods were insufficient for these cosmic tourists. The traditional naming conventions for comets and asteroids are built on the fundamental assumption that the object originated here, within our solar system. Their orbits are ellipses or circles, forever bound to our sun. An interstellar object shatters that assumption. Its path is not a closed loop, but a hyperbola, a trajectory that clearly shows it entered our system at an incredible speed, swung around the sun once, and is now heading back out into the deep, never to return. This profound difference in origin and destiny required a new classification. The International Astronomical Union had to create a new box to put these objects in because they simply didn't fit anywhere else. It's a quiet but powerful example of how a single discovery can force us to redraw the maps of our own cosmic backyard, acknowledging that we are not an isolated island, but a coastline on a vast star-strewn ocean. Now, let's look at the second part of that potential name, Atlas. Unlike comets of old, which were often named after the individual astronomers who first spotted them, like Halley or Hale-Bopp, most modern discoveries are credited to the robotic surveys that find them. Atlas is not a person, but an acronym for a powerful and vigilant system. This reflects a fundamental shift in how astronomy is done. Where once a single person could spend years gazing through an eyepiece, today we have automated telescopes that scan the entire sky every single night. These tireless robotic eyes can detect faint points of light moving against the backdrop of stars far more efficiently than any human. So when an object like a new comet or asteroid is found, the credit goes to the program, the system that made the discovery possible. It's a nod to the era of big data and collaborative, systematic sky searching that defines modern astronomy. The acronym ATLAS stands for the Asteroid Terrestrial Impact Last Alert System. Breaking this down reveals its primary and rather dramatic purpose. Asteroid is its main quarry. It's designed to find space rocks. Terrestrial impact clarifies the specific threat it's looking for. Asteroids on a collision course with Earth. And Last Alert speaks to its unique role. While other surveys search for large company-killer asteroids years or decades in advance, ATLAS is designed to find the smaller, city-sized impactors just weeks, days, or even hours before they might strike. It's the final line of defense, a planetary burglar alarm. Its goal is to provide enough warning for evacuation and preparation. The fact that it might also find a gentle visitor from another star is a beautiful, poetic bonus to its otherwise urgent and focused mission of planetary defense. Have you ever wondered about the unseen systems that protect our world while we sleep? It's a comforting thought, isn't it? This focus on planetary defense means that discovering an interstellar object is a wonderful and serendipitous byproduct of the ATLAS system's main job. Its mission is to take a wide, sweeping picture of the entire night sky accessible from its location, then do it again a few hours later, and again a few hours after that. Sophisticated computer software then compares these images, looking for anything that has moved. Most of the time, these moving dots are known asteroids or satellites. But occasionally, a new one appears. The system is designed for speed and coverage, not deep, targeted study. It is this constant, impartial vigilance, this relentless scanning of the heavens for anything out of the ordinary, that makes it so perfectly suited to catching a fleeting visitor from another star system, an object appearing without warning from an unexpected direction, just passing through on its long journey. The effectiveness of the ATLAS system comes from the fact that it is not just one telescope, but a coordinated global network. Originally composed of 2 telescopes in Hawaii, situated on Haleakala and Mauna Loa, the system expanded to include telescopes in South Africa and Chile. This geographic distribution is absolutely crucial. By having observatories in both the northern and southern hemispheres and spread out across different longitudes, the ATLAS network can provide continuous 24-hour coverage of the entire dark sky. When night ends in Hawaii, the sun is setting in Chile, and as daylight arrives there, South Africa is plunging into darkness. This seamless, around-the-clock observation means that a fast-moving object, like an incoming asteroid or a speedy interstellar comet, has nowhere to hide. It ensures that we never lose track of a potential threat or a scientific wonder simply because the sun came up in one part of the world. Before an object is confirmed to be interstellar and receives its I designation, it is first given a provisional name based on when it was found. This temporary name acts as a placeholder while its orbit is being calculated. For example, the second interstellar object, 2I/Borisov, was initially called C/2019 Q4 Borisov. This name is packed with information. The C indicated it was initially believed to be a comet. The 2019 was the year of its discovery. The Q refers to the 8th half-month of the year, in this case, the 2nd half of August. And the 4 meant it was the 4th such object discovered in that period. The name in parentheses, Borisov, credits its discoverer. Only after weeks of observation from telescopes around the world could astronomers plot its trajectory with enough precision to see that it was hyperbolic, proving it came from beyond our sun's influence and earning it the permanent and much more profound designation of 2I. Ultimately, this dual naming process tells the complete story of our encounter with a celestial visitor. The provisional name, like C/2019 Q4, is a snapshot of its arrival, the technical details of the moment we first laid eyes on it, a logbook entry of what and when. It's the initial report from the watchtower. But the permanent designation, like 2I Borisov, is the conclusion of the investigation. It is the object's confirmed identity, a label that speaks not just of its appearance, but of its origin, its nature, and its epic journey across unimaginable distances. It's the moment the object transforms from just another faint comet in a telescope to a confirmed messenger from another star. This transition from a temporary, data-driven label to a permanent, story-driven one reflects our own process of discovery, moving from initial suspicion and careful measurement to a final, wondrous confirmation. The very heart of Comet 3I Atlas, its nucleus, remains a profound mystery, forever shielded from our direct gaze. Unlike comets visited by spacecraft, we never saw its solid core up close. All our understanding is built on inference, like trying to guess the shape of a bell by only hearing its ring. Initial observations of its immense brightness led to breathtaking estimates. Some early calculations suggested a nucleus that could be several kilometers, perhaps even stretching to tens of kilometers in diameter. This would have placed it among the largest comets ever recorded, a true giant from another star system. This tantalizing possibility was based on a simple assumption, that its brightness was coming from a vast, stable surface reflecting sunlight. However, The comet's subsequent dramatic behavior would soon prove that the simplest explanation was not the correct one, and the true nature of its core was far more fragile and complex than its initial glow suggested. This giant nucleus, however, was not a single solid object. It was a betrayer of its own grand appearance. As astronomers watched, the heart of 3I Atlas began to crumble. In late March and early April of 2020, observations, including those from the Hubble Space Telescope, captured the comet in the act of self-destruction. The single point of light that represented its core resolved into a string of smaller, icy fragments, like a pearl necklace coming undone. This fragmentation event was the key to understanding its true nature. It revealed that the nucleus was not a monolithic block of ice and rock, but more likely a rubble pile, a loose agglomeration of smaller pieces held together weakly by gravity and frozen gases. The intense heat of our sun was simply too much for these fragile bonds, causing the entire structure to violently disintegrate, not just shed a little dust and gas, but to fundamentally break apart before our eyes. The material that made up this fragile, crumbling nucleus was surprisingly familiar. By analyzing the light from the comet's coma, the cloud of gas and dust surrounding the nucleus, scientists could determine its chemical makeup. They found the spectral signatures of common cometary ices like water, carbon monoxide, and carbon dioxide, all mixed with fine silicate dust. What was astonishing was not what they found, but what they didn't find. There were no exotic, truly alien materials. The building blocks of 3I Atlas appeared to be remarkably similar to the comets born and raised in our own solar system, particularly those from the distant Oort cloud. This suggested that the chemistry of planetary system formation might be quite universal. The same basic ingredients that built our own cosmic neighborhood seem to be at work around other stars, a comforting thought that connects our solar system to the vast, unknown stellar nurseries from which this visitor came. Surrounding this disintegrating core was the comet's most visible and ethereal feature, its coma. The coma is the beautiful, glowing atmosphere that gives a comet its fuzzy, ghost-like appearance. It's not part of the solid body, but a temporary shroud created by the comet's own activity. As 3I Atlas raced toward the sun, solar radiation warmed its nucleus, causing the frozen gases to sublimate, turning directly from solid ice into gas. This process, like dry ice creating fog on a stage, released a torrent of gas and dust that expanded outwards into space. This cloud, the coma, is what we actually see from Earth.
For 3I Atlas, its coma was initially so bright and active that it completely outshone its tiny nucleus, creating the illusion of a much larger object and hiding the fragility that lay within its glowing, temporary atmosphere. The scale of a comet's coma can be truly mind-boggling, and 3I Atlas was no exception.
While its nucleus was likely only a few kilometers across at most, its coma swelled to an immense size. At its peak, the cloud of gas and dust that formed its temporary atmosphere stretched for hundreds of thousands of kilometers. To put that into perspective, the coma was easily larger than the planet Jupiter and possibly even approached the diameter of the Sun itself. It's a remarkable paradox of the cosmos. A tiny, city-sized chunk of ice can produce a transient atmosphere that dwarfs the largest planets in our solar system. This vast, tenuous cloud is almost entirely empty space, with particles spread incredibly thin. But because it catches and reflects sunlight over such a huge area, it becomes a beacon visible across millions of miles, a testament to the powerful interaction between a small, frozen traveler and a star. Many comets are famous for the beautiful greenish hue of their comas, a color that seems almost supernatural. This distinctive tint is not from the ice or dust itself, but from a delicate chemical process occurring in the vacuum of space. The green glow is the signature of diatomic carbon, a simple molecule made of two carbon atoms bonded together, along with another molecule called cyanogen. When these molecules are released from the nucleus, they are bombarded by ultraviolet light from the sun. This excites them, and as they release that extra energy, they fluoresce, emitting light in a very specific, narrow green part of the spectrum. Observations of 3I/Atlas did indeed show this characteristic green color in its coma, confirming that this common cometary process was at play. This green glow is also famously fragile. The same solar radiation that creates it also breaks the molecules apart, which is why the green color is almost always confined to the comet's head and never extends into its tail. The formation of the coma for 3I Atlas was a process of incredible violence and speed. It wasn't a gentle, steady misting of gas from the nucleus. Instead, the data suggests it underwent a massive outburst, a singular, energetic event that caused its brightness to surge dramatically. This likely happened when a large, fresh surface of highly volatile ices, perhaps buried deep within the nucleus, was suddenly exposed to direct sunlight. This could have been caused by a landslide or the breaking off of an outer crust. The result was a runaway sublimation event, where enormous quantities of frozen gases, like carbon monoxide, flashed into vapor almost instantly. This explosive outgassing propelled an immense amount of dust and gas into space in a very short period, creating the vast, dense coma that first drew so much attention and led to the initial, and ultimately incorrect, estimates of its enormous size. The true size of the nucleus became a central puzzle. How could something so bright be so fragile? The answer lies in the difference between sustained brightness and outburst brightness. The initial calculations that pointed to a nucleus tens of kilometers wide were based on the comet's absolute magnitude, a measure of its intrinsic brightness. This works well for inactive asteroids or stable comets. However, 3I Atlas was not stable. Its immense brightness wasn't coming from sunlight reflecting off a large, solid surface. Instead, it was coming from an enormous, dense cloud of dust that had been recently ejected, a cloud that was temporarily catching and reflecting sunlight far more efficiently than the tiny nucleus ever could. Once the comet began to fragment, its brightness plummeted, revealing the truth. The nucleus was not a giant, but likely a small, perhaps kilometer-scale body that had put on a spectacular but fleeting show. One must wonder if the comet's interstellar journey itself was responsible for its profound fragility. For millions, perhaps billions of years, 3I Atlas drifted through the cold, empty space between stars. During this immense voyage, it would have been subjected to a constant drizzle of high-energy cosmic rays. This relentless radiation can penetrate deep into the ice, altering its chemical structure, breaking down complex molecules, and potentially creating pockets of trapped volatile gases. Furthermore, passing through giant molecular clouds or near other stars could have induced thermal stresses. It's conceivable that this long journey didn't strengthen it, but instead made it brittle and unstable. It arrived in our solar system preconditioned to fail, like an ancient piece of porcelain that looks solid but shatters at the slightest touch of warmth from our sun. Its dramatic demise may have been the final chapter in a story of slow decay that began long ago in the darkness between the stars. A key diagnostic that astronomers use to understand a comet's nature is the ratio of dust to gas being emitted from its nucleus. This tells a story about its formation and evolution. For 3I Atlas, measurements of its coma revealed a very high dust-to-gas ratio, meaning it was expelling a great deal of dust for the amount of gas it was producing. This is characteristic of comets that are rich in carbon monoxide ice. Carbon monoxide is extremely volatile and sublimates at very low temperatures, far out from the sun. As this gas erupts, it has the energy to lift and carry a lot of dust particles with it. This finding further supported the idea that its bright outburst was driven by the sudden exposure of these volatile ices. It also provided another piece of the puzzle, suggesting its home star system may have had a chemistry that favored the formation of such carbon monoxide-rich, dusty bodies. It's fascinating how a cloud of dust and gas, viewed from so far away, can tell us so much about the specific conditions of a place we may never see. Does thinking about these vast, silent journeys through space make you feel more peaceful here in your bed? The most fundamental tool NASA will use to decode the secrets of Interstellar Comet 3I/Atlas is not a camera in the traditional sense, but a spectrograph. This instrument acts like a celestial prism, taking the faint, reflected sunlight from the comet's atmosphere, or coma, and splitting it into its constituent colors, a rainbow of data. Within this spectrum, dark lines and bright bands appear, which are the unique chemical fingerprints of the atoms and molecules present. Each element and compound absorbs and emits light at very specific wavelengths. So by analyzing this pattern, scientists can create a complete inventory of the comet's composition without ever touching it. They can identify not just water, but carbon monoxide, cyanide, and complex organics from hundreds of millions of miles away. This technique is so sensitive that it can reveal the temperature, density, and even the velocity of the gases as they stream away from the nucleus, painting a vivid picture of the physical processes at play in this visitor from another star. One of the first and most crucial molecules scientists would search for in the spectral data from 3I Atlas is carbon monoxide. This isn't just because it's a common molecule, but because it is an extraordinary cosmic thermometer. Unlike water ice, which begins to sublimate and turn into gas relatively close to the sun, carbon monoxide is incredibly volatile and will start to vaporize at extremely low temperatures when the comet is still deep in the outer reaches of our solar system. If NASA detects a strong carbon monoxide signature while 3I Atlas is still farther out than Jupiter or Saturn, it provides a powerful clue about its birthplace. It suggests the comet formed in a frigid, distant region of its home planetary system, a place so cold that this volatile gas could be trapped as ice. The ratio of carbon monoxide to water would tell a story about the temperature and chemistry of a protoplanetary disk light years from our own. Beyond the more common gases, a key focus would be on unusual molecules like diatomic carbon, or C2. This molecule consists of just two carbon atoms bonded together and glows with a distinct greenish hue in the comas of comets from our own solar system. However, its origin is a long-standing puzzle. It's not thought to be stored as C2 ice in the nucleus itself, as it's too reactive. Instead, scientists believe it's the broken-down remnant of more complex, carbon-rich parent molecules, perhaps long organic chains or rings that are blasted apart by solar radiation. By carefully measuring the amount of C2 in the coma of 3I Atlas and mapping its distribution, NASA could work backwards to deduce the nature of these mysterious parent molecules. If the C2 abundance is wildly different from our own comets, it could signal a fundamentally different type of organic chemistry in the building blocks of its home world. Perhaps the most profound measurement NASA would attempt is of the comet's isotopic ratios, which serve as an unforgeable passport from its star system of origin. An isotope is a variant of an element with a different number of neutrons. For example, deuterium is a heavy version of hydrogen. The ratio of deuterium to regular hydrogen in water ice is determined by the specific temperature and conditions of the primordial cloud where a solar system forms. Our own solar system has a characteristic range of these D/H ratios. By measuring this ratio in the water vapor sublimating from 3I/Atlas, scientists could directly see if its home nebula was similar to our own or vastly different. A match would suggest the raw materials for solar systems are fairly uniform across the galaxy. A mismatch, however, would be a stunning revelation, proving that planetary systems can be born from clouds with fundamentally different starting chemistries. Another deceptively simple yet deeply informative measurement would be the comet's dust-to-gas ratio. As 3I Atlas approaches the Sun, its ices will sublimate into gas, and this expanding gas will drag dust particles off the surface with it. By observing the brightness of the coma in different wavelengths of light, scientists can distinguish the sunlight reflected by dust from the light emitted by gas. This allows them to calculate the proportion of each. This ratio is not random. It's a fossilized record of where in its original protoplanetary disk the comet formed. Regions closer to a young star tend to have different proportions of ice and rock than regions farther out. By comparing the dust-to-gas ratio of 3I Atlas to our own comets, we could infer whether it was formed in an environment analogous to our Kuiper belt or in a much dustier or icier region of its alien solar system. Going deeper than just the amount of dust, NASA would analyze the very nature of the dust grains themselves. This involves looking at how they scatter sunlight and emit thermal radiation. From this data, scientists can determine if the dust is made of fluffy, porous aggregates, like cosmic dust bunnies, or solid, dense little rocks. They can also identify the minerals within, looking for the spectral signatures of silicates like olivine and pyroxene. A critical question would be whether these silicates are crystalline or amorphous. Amorphous silicates have a disordered atomic structure, indicating they've remained pristine and cold since their formation. Crystalline silicates, however, require high temperatures to form, implying this dust was once heated near its parent star before being transported to the frigid outer disk where the comet assembled. This would reveal dynamic mixing processes in another solar system. In the near-perfect vacuum of space, the thin gas of a comet's coma is a strange and wonderful laboratory. Here, atoms can emit light in ways that are impossible to replicate in a dense atmosphere like Earth's. These are called forbidden lines. An atom, such as oxygen, can be energized by sunlight and get stuck in a high-energy state. On Earth, it would quickly bump into another atom and lose that energy. But in the coma, it can stay in this state for seconds or even minutes before finally relaxing and emitting a photon of light at a very specific, forbidden wavelength. For NASA scientists studying 3I Atlas, these faint glows are treasure. The forbidden lines of oxygen, for example, provide an exceptionally clean way to measure how much water is coming off the nucleus, as they are directly produced by the breakdown of H2O molecules, free from contamination from other chemical sources. A truly prized discovery in the composition of 3I Atlas would be the detection of noble gases like argon, krypton, or xenon. These elements are famously inert. They do not like to react with anything. Because of this, they can only be trapped inside a comet's water ice when it forms at extraordinarily low temperatures, far colder than is required to trap even carbon monoxide. Finding these gases and measuring their abundance relative to water would provide the most precise thermometer reading possible for the comet's formation environment. It would tell us the exact temperature of the specific region in its parent nebula where it was born, perhaps as low as -240 degrees Celsius or just 30 degrees above absolute zero. Such a measurement is incredibly difficult, as the signals are weak, but it would provide an unparalleled glimpse into the coldest, most distant nurseries of planetary systems. One of the most ambitious and tantalizing goals in studying 3I/Atlas would be the search for a property called chirality in its organic molecules. Many complex molecules, including the amino acids that form proteins in life on Earth, can exist in two mirror image forms, like a left hand and a right hand. For reasons we don't fully understand, life on our planet exclusively uses the left-handed versions of amino acids. Could this preference have come from space? To find out, astronomers would use a technique called polarimetry. They would measure how the dust in the comet's coma twists the light that reflects off of it. A systematic twisting of the light would indicate an excess of either left or right-handed molecules. Finding such a bias in a visitor from another star system would be a monumental discovery, suggesting that the molecular precursors to life with a built-in handedness might be a common feature throughout the galaxy. While we talk about a comet being a dirty snowball, confirming the presence of water ice is surprisingly indirect. The dark, dusty surface of the nucleus reflects so little light that it's nearly impossible to see the spectral signature of ice directly on its surface. Instead, scientists typically prove water is there by observing its breakdown products in the coma, primarily the hydroxyl radical, OH. For an object as significant as Interstellar Comet 3I Atlas, NASA would use multiple methods to not only confirm water, but to understand its history. They would want to determine if the ice is amorphous, a disordered, glassy state that forms at very low temperatures, or crystalline, like a snowflake. Amorphous ice, when warmed for the first time, can release a burst of trapped gases. Detecting such a change as the comet nears the Sun would tell us that 3I Atlas has remained a pristine frozen relic from its formation, a truly unaltered piece of another star's planetary cradle. Does thinking about these distant, icy worlds make you feel a sense of connection to the wider universe? Or does it emphasize how unique our own little corner of space is? The path of 3I/Atlas through our solar system was not a closed loop, like the orbits of planets or even long-period comets from our own Oort cloud. Instead, it traced a distinct and dramatic shape known as a hyperbolic trajectory. This is the definitive signature of a true interstellar visitor. Imagine throwing a stone past a massive sphere. It curves around it, but has too much energy to be captured into a circle. It arrives from one direction, bends its path, and departs in another, never to return. This open-ended path is a mathematical certainty for objects with enough velocity to overcome a star's gravitational pull. For astronomers, detecting this specific hyperbolic shape was the first and most crucial piece of evidence that 3I Atlas was not one of our own, but a celestial nomad passing through our cosmic neighborhood on a one-time journey. It was a fleeting guest, and its trajectory was its calling card, announcing its origins from the vast, dark expanse between the stars. The mathematical measure that defines this open-ended path is called orbital eccentricity. For any object trapped in a perfect circular orbit, like a planet might ideally have, its eccentricity is 0. For an elliptical orbit, like that of Halley's Comet, the value is between 0 and 1. But for an object to be on a hyperbolic, escape trajectory, its eccentricity must be greater than 1. The calculated eccentricity for 3I Atlas was significantly higher than 1, settling around a value of 1.006. While this number may seem only slightly above the threshold, in celestial mechanics, it is an enormous and unambiguous difference. It's the cosmic equivalent of a locked door versus a door wide open to infinity. This single value, derived from countless observations of its position against the background stars, confirmed it possessed more than enough energy to escape the Sun's gravity forever. It was fundamentally unbound to our solar system. This ability to escape is entirely due to its incredible speed. As it cruised through the inner solar system, 3I Atlas was traveling at a breathtaking velocity. When far from the Sun, its speed relative to our star was about 26 kilometers per second, which is nearly 60,000 miles per hour. This is a speed so immense that the Sun's gravity, which holds planets like Jupiter and distant Neptune in their orbits, could only bend its path, not capture it. To put this into perspective, NASA's Voyager 1 spacecraft, our fastest emissary to interstellar space, is traveling at about 17 kilometers per second. This comet arrived in our system already moving faster than our fastest ever outbound probe. This initial velocity is what it carried with it from its journey across interstellar space, a momentum gathered from its birth around another star and its long, dark travels. This speed was the engine driving its hyperbolic journey, ensuring its visit would be a temporary one. The angle of its approach was also quite dramatic, adding a third dimension to its celestial flyby. 3. Atlas did not enter our solar system along the relatively flat plane where the planets orbit, known as the ecliptic. Instead, it plunged in from above at a steep inclination of roughly 130 degrees relative to this plane. This means it was essentially traveling backward compared to the direction the planets orbit the Sun. Such a retrograde and highly inclined path is another strong indicator of an external origin. Objects born from our Sun's protoplanetary disk tend to orbit in the same direction and on roughly the same plane. The comet's trajectory, therefore, was like a ship crossing a busy roundabout from a completely unexpected overpass, highlighting just how independent its journey was from the established traffic patterns of our own solar system's celestial bodies. It was truly an outsider, obeying only the laws of gravity as it cut across our familiar cosmic plane. The climax of its journey through our system was its perihelion, the point of its closest approach to the Sun. This occurred on May 25, 2020. At that moment, the interstellar comet was approximately 23 million miles, or 37 million kilometers, from our star. This is closer to the Sun than the planet Mercury. During this close pass, it was subjected to an immense barrage of solar radiation and gravitational stress. The intense heat would have rapidly vaporized its surface ices, and the powerful tidal forces from the Sun's gravity would have pulled and twisted its nucleus. This perihelion passage was the most violent and transformative part of its visit, likely contributing significantly to the fragmentation event that was observed just weeks earlier. It was a fiery and fleeting embrace with a star that was not its own, a moment of maximum velocity and maximum stress before it was flung back out into the cold darkness. Imagining such a close, fiery encounter with our own star is quite humbling. Does thinking about these vast cosmic journeys ever make you feel a sense of wonder right before you drift off to sleep? The Sun's gravity acted like a massive, silent engine, performing a gravitational slingshot on the comet. As 3I Atlas fell inward toward the Sun, it continuously accelerated, converting its potential energy into kinetic energy. It reached its maximum speed precisely at perihelion. Then, as it swung around the Sun and began to climb back out of the star's gravity well, that process reversed. The Sun's pull began to slow it down. However, because it arrived with so much initial velocity, it would never slow down enough to be captured. The Sun's gravity, in effect, grabbed the comet, sharply redirected its path, and then threw it back out into space, but on a different heading and with its interstellar velocity largely intact.
This gravitational assist is a maneuver we use with our own spacecraft, but here we witnessed nature performing it on a visitor from another star system, a perfect demonstration of gravitational physics on a grand scale. By tracing its trajectory backward in time, astronomers could determine the direction from which 3I Atlas arrived.
Its radiant point, the spot in the sky it appeared to emanate from, was located in the constellation Triangulum Australe, the Southern Triangle. This small constellation is visible primarily from the southern hemisphere. While this doesn't mean the comet originated from a star within that specific constellation, as constellations are just patterns of stars at vastly different distances, it gives us a precise origin point on our celestial sphere. It tells us the direction of its long journey toward us. For millennia, it had been silently moving through the Milky Way from that patch of sky, an invisible messenger on a course that would, for a brief moment, intersect with our own solar system before it continued its endless pilgrimage through the galaxy. Just as we know where it came from, we can also predict where it is going. After whipping around the sun, its new outbound trajectory is sending it careening towards the constellation Puppis, part of the larger ancient constellation of Argo Navis, the ship of Jason and the Argonauts. It will travel for thousands of years, covering unfathomable distances, before it might ever approach another star system. For all intents and purposes, it is heading back into the great unknown, the interstellar medium. Its encounter with our sun has forever altered its path. It is not leaving on the same vector it arrived on. Our solar system has left a permanent mark on its journey, changing its cosmic itinerary. It carries with it a memory of our sun's warmth and gravitational influence as it recedes from us, eventually becoming just another faint, frozen wanderer in the void between the stars. The comet's speed was not constant throughout its visit. It was in a constant state of flux, dictated entirely by its distance from the sun. As it fell from the outer reaches of the solar system inward, its velocity steadily increased, day by day, hour by hour. This acceleration peaked at perihelion, where it was moving at its fastest. Then, as it began its long climb away from the sun, it started to decelerate. This gravitational braking will continue for thousands of years, but it will never be complete. It will slow down, but it will always retain a positive velocity relative to our sun. Eventually, as it gets so far away that the sun's gravity becomes negligible, its speed will settle back to its original interstellar cruising velocity of around 26 kilometers per second, ready for its next long, dark voyage across the galaxy. The certainty with which astronomers could map this trajectory might seem surprising, given that 3I Atlas was only observed for a few months. This confidence comes from the power of collective global astronomy. Observations from dozens of telescopes, both on the ground and in space, were pooled together. Each data point, a precise measurement of the comet's position at a specific time, helped to refine the orbital solution. Powerful computers ran complex simulations, fitting the data to various models. The result was unequivocal. Only a hyperbolic orbit perfectly matched all the observations. The margin of error was so small that the possibility of it being a native Oort cloud object on a peculiar path was statistically ruled out. It was a definitive piece of celestial detective work, proving beyond any reasonable doubt that humanity had just witnessed a fleeting visit from a true interstellar object. The study of an interstellar traveler like 3I/Atlas would offer a priceless window into the architecture of an alien solar system. The comet's trajectory, its immense speed, and the precise angle of its entry into our system are not random. They are the final chapter in a story of gravitational violence that happened long ago and light years away. By rewinding its path, astronomers could deduce the forces that cast it out of its home. A very high ejection speed might point to a chaotic dance between multiple Jupiter-sized planets, their gravitational fields acting like a slingshot. A slightly more gentle exit could imply the influence of a binary star companion, its long, slow orbit destabilizing the outer comet cloud. This analysis turns the comet from a simple object into a fossil record of planetary migration and system stabilization, giving us a clearer picture of the massive unseen worlds that likely still orbit its parent star, and the dramatic processes that shape how planetary systems mature across the galaxy. Its arrival would also serve as a crucial test for a fundamental assumption in science, the universality of chemistry. We assume the raw materials that built our solar system are common throughout the cosmos, but this is largely based on studying light from distant stars. 3I Atlas would be a physical sample, a tangible piece of another world's chemistry delivered to our cosmic doorstep. Scientists would eagerly train spectrographs on its coma, the gassy halo that forms as it warms up, to read its chemical fingerprint. The goal would be to measure the ratios of key isotopes, such as the amount of heavy water containing deuterium compared to normal water. These isotopic ratios are like a planetary system's DNA. Finding a ratio similar to our own comets would be a profound confirmation that our sun was born from a similar type of interstellar cloud as its parent star. A wildly different ratio, however, would be even more exciting, suggesting that different regions of the galaxy have distinct chemical compositions, and that planetary systems can be built from a surprisingly diverse menu of ingredients. While familiar molecules like water and carbon monoxide are expected, the true scientific treasure hidden within 3I Atlas would be the potential for discovering exotic compounds rarely seen in our own system. Its parent star might have been born in a nebula unusually rich in elements like nitrogen or sulfur, leading to the formation of unique ices and organic molecules on the comet's surface. The hunt would be on for complex organics, especially prebiotic molecules that serve as the building blocks for amino acids and sugars. Finding such compounds would add immense weight to the theory of panspermia, the idea that life's ingredients are not unique to Earth but are constantly being ferried between star systems by these interstellar messengers. The comet would transform from a celestial novelty into a potential carrier of the very seeds of life, suggesting that the potential for biology is seeded throughout the galaxy, just waiting for the right conditions on a welcoming world. The simple act of confirming a third interstellar object would have profound statistical importance. Before the discovery of 1I Oumuamua and 2I Borisov, astronomers' estimates for how many of these objects pass through our solar system were largely theoretical and generally quite low. The arrival of two such objects in just a few years suggested they might be far more common than we ever imagined. The discovery of 3I Atlas would provide a third crucial data point. This would allow scientists to move from educated guesswork to statistically sound estimates of the population density of these interstellar wanderers. It would help answer a key question: is our solar system constantly swimming in a dilute sea of debris from other stars, or are these visits truly once-in-a-generation events? Knowing this number is vital for understanding how much material is exchanged between star systems and how planetary systems pollute their galactic neighborhoods. The detection of a comet like 3I/Atlas would immediately trigger a worldwide astronomical fire drill, serving as a critical test of our planetary defense and rapid response capabilities. As soon as its interstellar nature was confirmed, observatories across the globe and in space would scramble to coordinate observations. The Vera C. Rubin Observatory in Chile, designed specifically to detect such objects, would work in concert with space telescopes like Hubble and the James Webb Space Telescope. This scenario would test our ability to share data in real time, to make swift decisions on how to allocate precious telescope time, and to deploy different instruments to capture every possible piece of information before the visitor vanished back into the void. The lessons learned in this global exercise of coordination and collaboration would be invaluable, preparing humanity for the next interstellar guest, which might be even more scientifically significant or on a trajectory that requires even faster analysis. Beyond its chemical composition, 3I Atlas would provide a direct look at the physical properties of planet-building materials from another star system. As it made its closest approach to our Sun, it would endure intense solar radiation and heat. Scientists would watch intently to see how it responded. Would it hold together, suggesting it was made of a dense, resilient material, perhaps formed closer to its parent star? Or would it begin to crumble and disintegrate, much like the fragile Oort cloud comet C/2019 Y4 Atlas famously did? This observation would be a direct probe into the material science of an alien protoplanetary disk. The comet's structural integrity, or lack thereof, would reveal whether the primordial building blocks of its home system were sturdy cosmic bricks or delicate fluffy snowballs, offering clues as to how easily planets could form and grow around other stars. The very makeup of the ices in 3I Atlas could hold subtle clues about the type and age of its parent star. A high abundance of extremely volatile ices, like frozen carbon monoxide or nitrogen, which vaporize at very low temperatures, would suggest the comet formed in the incredibly cold outer reaches of its system, far from its star. Conversely, a noticeable lack of these same ices might imply it spent a long time being gently baked in a warmer region, or that its parent star was much hotter and brighter than our Sun. By analyzing the cocktail of its sublimating gases, astronomers could build a chemical profile and work backwards. This forensic chemistry would allow them to speculate on the nature of the star it once called home. Was it a small, cool red dwarf, or a bright, sun-like star, without ever having seen a single photon of its light? For millions of years, as 3I Atlas tumbled through the vast, empty space between the stars, its surface was not untouched. It was relentlessly bombarded by high-energy cosmic rays and abraded by microscopic dust particles floating in the interstellar medium. This eons-long journey would have created a distinct, weathered crust on the comet, a sort of space tan that is chemically different from the pristine material locked in ice beneath. As the comet neared our Sun and began to outgas, jets would burst from its surface, ejecting that deeper, untouched material. By comparing the composition of the weathered surface to the fresh ice from the interior, scientists could read the history of its journey. The comet itself would become a probe, carrying a physical record of the density, radiation levels, and chemical composition of the lonely galactic voids it traversed. Before we started finding these visitors, we had only one solar system to study in detail, our own. 2I Borisov was the first interstellar comet, and it provided a second data point, looking remarkably similar to our own comets. The discovery of 3I Atlas would provide the third and perhaps most important data point. In science, 2 points simply form a line, but 3 points begin to reveal a true pattern, or a lack thereof. Would 3I Atlas also look familiar, suggesting that comet formation follows a standard model across the galaxy? Or would it be profoundly different, more like the strange rocky Oumuamua, indicating that the galaxy is filled with a wild diversity of small bodies? This third visitor would be the tiebreaker, allowing us to move from simple comparison to genuine statistical analysis of how planetary systems are born and whether our own solar system is common or an oddity. While it would be practically impossible to design, build, and launch a spacecraft to intercept 3I Atlas during its brief passage through our system, its discovery would provide the ultimate justification for funding a mission to meet the next one. Projects like the European Space Agency's Comet Interceptor are already being designed for precisely this scenario. The mission involves 3 spacecraft that would launch and then wait patiently in a stable orbit, like a sprinter in the starting blocks. The rich data gathered from studying 3I Atlas from afar would give engineers the precise information they need to finalize the mission's design and instruments. Its flyby would be the final, compelling argument to politicians and funding agencies, ensuring that when 4I is inevitably detected, humanity will be ready to dispatch a robotic ambassador to rendezvous with it, offering us our first chance to fly through and directly sample a piece of another solar system. To truly understand a visitor like the hypothetical interstellar comet 3I Atlas, NASA wouldn't rely on a single instrument, but a cascade of increasingly powerful observatories, beginning with wide-field survey telescopes. The first detection would likely come from an automated sky survey, such as the Atlas system itself or the forthcoming Vera C. Rubin Observatory in Chile. This observatory is a marvel of engineering, designed to image the entire visible southern sky every few nights with its enormous 3.2 gigapixel camera. Its primary mission is to detect transient and moving objects. An object like 3I/Atlas would first appear as a faint new point of light in its data stream. Sophisticated software would flag it as an unknown object, automatically comparing its position over several nights to calculate a preliminary orbit, providing the very first hint that this tiny wanderer was not gravitationally bound to our Sun, but was merely passing through our cosmic neighborhood on its own epic journey. Once a candidate interstellar object is flagged, a global rapid response network is activated. The Minor Planet Center, the worldwide clearinghouse for such observations, would broadcast an alert to observatories across the planet. Astronomers, both professional and amateur, would race to point their telescopes at the specified coordinates. This immediate follow-up is absolutely critical. Each new observation from a different location on Earth helps to refine the object's trajectory with breathtaking precision. It's a process of triangulation on a cosmic scale. Within hours to days, dozens of data points would confirm the object's hyperbolic orbit, the unique signature of an interstellar traveler. This collaborative global effort isn't just about confirmation. It's about building a precise enough timeline to know exactly where and when to point our most powerful instruments, like Hubble and Webb, before the comet fades back into the darkness. To get the sharpest possible view of 3I/Atlas, astronomers would immediately turn to the Hubble Space Telescope. Orbiting high above the distorting effects of Earth's atmosphere, Hubble can achieve a resolution that ground-based telescopes can only dream of. Its powerful optics could potentially resolve the comet's solid nucleus from the glowing gas and dust of its coma. This allows scientists to measure the nucleus's size and watch for any changes, such as sudden brightening that might indicate an outburst, or even fragmentation as it warms near the Sun. Furthermore, Hubble's ultraviolet instruments are essential for studying the composition of the coma. Many important molecules, like water and carbon monoxide, are best observed by the specific wavelengths of ultraviolet light they emit or absorb, signatures that are completely blocked by our planet's ozone layer. Hubble provides a window into the comet's chemistry that is forever closed to us on the ground. The James Webb Space Telescope would offer an entirely new dimension to the study of 3I Atlas, observing it in the infrared spectrum. This is the language of heat and of complex, life-bearing molecules. While Hubble excels at seeing the hot gases in the coma, Webb would be able to peer through that glowing shroud to study the cooler dust and even measure the thermal emission from the nucleus itself, giving a direct reading of its temperature and surface properties. Webb's unparalleled sensitivity would allow it to detect the faint infrared signatures of complex organic molecules, the very building blocks of life that might be vaporizing from the nucleus. It could identify specific types of ices like water, carbon dioxide, and methane with far greater certainty than any other instrument. Observing 3I Atlas with Webb would be like giving a sample of another solar system a full forensic chemical analysis from hundreds of millions of miles away. One of the most powerful tools for deciphering a comet's secrets is spectroscopy, the art of breaking light down into its constituent colors. When sunlight reflects off the gas and dust in the comet's coma, the atoms and molecules within it absorb and re-emit light at very specific frequencies, creating a unique chemical barcode. By capturing the comet's light and passing it through an instrument called a spectrograph, astronomers can read this barcode. They can identify not just the presence of elements like oxygen and carbon, but complex molecules like cyanogen or ammonia. This technique reveals the raw ingredients that were present in the distant protoplanetary disk where 3I Atlas formed billions of years ago. It's a form of cosmic archaeology, telling us if the chemistry that led to our own solar system is common throughout the galaxy. Does the night sky ever make you feel a sense of profound wonder about what else might be out there, made of the very same elements? Beyond visible and infrared light, astronomers would use vast arrays of radio telescopes, like the Atacama Large Millimeter/Submillimeter Array, or ALMA in Chile. ALMA doesn't see starlight. It detects the faint, low-energy radiation emitted by cold molecules and dust. This makes it exceptionally good at studying the deep, cool interior of a comet's coma, far from the sun's direct heat. ALMA could map the distribution of molecules like carbon monoxide with incredible precision, revealing the structure of jets spewing from the nucleus. By analyzing the Doppler shift in the radio waves, it can even measure the velocity of the outgassing material, essentially creating a 3D weather map of the coma. This provides invaluable clues about the nucleus's rotation and the location of its active regions. It's a way of sensing the comet's breath, feeling the pulse of its activity as it responds to the warmth of our sun. A more direct and active method of investigation involves planetary radar. Using enormous dishes like the Goldstone Solar System radar in California, astronomers could send a powerful beam of radio waves hurtling towards 3I Atlas. By timing how long it takes for the echo to return and analyzing the changes in the signal, they can construct an astonishingly detailed picture of the comet's nucleus. Radar can determine its precise size, shape, and rotation period with an accuracy that optical telescopes cannot match. More than that, the way the radio waves scatter can reveal the texture of the surface, whether it is smooth and compacted or rough and porous, perhaps even covered in boulders. This technique essentially allows scientists to touch the comet with radio waves, creating a 3D model of this alien object without ever leaving Earth, a process that feels like a quiet and gentle form of interstellar echolocation. A much more subtle yet powerful technique that would be employed is polarimetry. Sunlight, as it travels through space, is unpolarized, meaning its light waves vibrate in all directions. However, when this light bounces off the tiny dust grains in a comet's coma, it becomes polarized, with the waves tending to vibrate in a specific direction. By measuring the angle and amount of this polarization, astronomers can learn a great deal about the physical nature of those unseen dust particles. It can tell them about the particles' size, their shape, whether they are spherical or elongated and fluffy, and even their composition, distinguishing between icy grains and rocky silicate material. It's a remarkably clever method of remote analysis. It's like trying to understand the sand on a distant beach simply by studying the quality of the light glinting off its surface, revealing the secrets of its texture and makeup from afar. While launching a dedicated intercept mission to a newly discovered interstellar comet would be nearly impossible given the time constraints, NASA and other space agencies would certainly investigate using existing spacecraft for a potential flyby. They would meticulously check the trajectories of every active probe in the solar system, from solar observatories to asteroid explorers like Lucy or Psyche, to see if any could be slightly redirected for a distant encounter. Even a flyby from millions of miles away would be scientifically invaluable, providing a completely different viewing angle than what is possible from Earth. in situ perspective could reveal details about the comet's dust tail and ion tail that are invisible from our vantage point. It would be a mission of opportunity, a serendipitous bonus that could provide data we never expected to gather, turning a pre-existing mission into a pioneering interstellar explorer. Finally, the study of 3I Atlas would not be limited to a few major observatories. The global community of amateur astronomers would play an indispensable role. Today, skilled amateurs possess equipment, from telescopes to sensitive cameras and spectrographs, that would have been the envy of professional institutions just a few decades ago. This network of dedicated skywatchers provides near continuous 24-hour monitoring of the comet. While the large professional telescopes have limited, scheduled time, amateurs can track the comet night after night, capturing its subtle changes in brightness, the development of its tail, and any unexpected outbursts. This constant stream of data is vital for building a complete picture of the comet's behavior. It turns the observation of this rare visitor into a truly global, collaborative effort, uniting people from all walks of life in the shared pursuit of cosmic understanding. When we place 3I/Atlas alongside its interstellar predecessors, the differences in their journeys become immediately apparent. The path of any object through space is defined by its orbital eccentricity, a number that tells us how stretched its orbit is. For a captured object, like a planet or a solar system comet, this value is less than 1. For an interstellar visitor, it must be greater than 1, indicating an open hyperbolic path. Oumuamua's eccentricity was about 1.1. 2, just enough to prove it was unbound to our Sun. Comet Borisov raised the bar significantly with an eccentricity of roughly 3.36, indicating a much higher speed as it entered our system. The preliminary data for 3I Atlas, however, suggest an eccentricity that may be even greater, perhaps the highest ever recorded for any object. This extreme value hints at a truly powerful ejection from its home star system, a gravitational slingshot of immense force that sent it hurtling through the void at incredible velocity, a cosmic testament to the dynamic and sometimes violent nature of planetary system formation far, far away. Beyond its path, the sheer scale of 3I Atlas sets it profoundly apart from the other visitors we've hosted. Oumuamua was an enigma in its shape and size, thought to be a strangely elongated object, perhaps a few hundred meters long but only tens of meters wide, a cosmic needle in a haystack. The second visitor, Borisov, was more familiar, presenting as a typical comet with a nucleus estimated to be around 1 kilometer in diameter. 3I Atlas, in stark contrast, is believed to be a true giant. Early estimates place its nucleus at a colossal 10 kilometers or more in diameter, potentially making it an interstellar megacomet. This isn't just a quantitative difference, it's a qualitative one. An object this large is not just a fragment. It could be a fundamental building block of a planet, a nearly pristine protoplanetary body that carries a vast reservoir of information from its home system, making it less of a messenger and more of a library. This vast difference in size translates directly into a difference in composition and potential for discovery. Oumuamua baffled scientists because it showed no signs of a coma or tail. It released no visible gas or dust as it passed the Sun, leading to speculation that it was a dry, rocky body, or perhaps something even more exotic, like a nitrogen iceberg. Comet Borisov, on the other hand, was unambiguously active. It outgassed water and, most revealingly, an unusually high concentration of carbon monoxide. This suggested it formed in an extremely cold, carbon monoxide-rich environment far from its parent star. 3I Atlas, by virtue of its immense size, is expected to be a treasure trove of pristine volatiles. Its vast interior would have been shielded from cosmic radiation for eons, preserving a perfect chemical snapshot of its native stellar nebula. The sheer volume of material it could release would offer an unprecedented opportunity to analyze the raw ingredients of another solar system in stunning detail. The way these objects move is also telling. Oumuamua exhibited a tiny but distinct non-gravitational acceleration, a slight push that couldn't be explained by the sun's gravity alone. Without a visible coma, this acceleration remains one of its greatest mysteries. Borisov also showed a slight push, but it was perfectly consistent with the gentle jetting of gas and dust from its surface, a classic cometary behavior. For 3I Atlas, the observation of any non-gravitational forces would be monumental. Given its enormous mass, any detectable push would have to be the result of truly stupendous levels of outgassing, far beyond anything seen from Borisov. By measuring the strength of this push and analyzing the specific gases causing it, scientists could paint a detailed picture of its internal engine, learning not just what it's made of, but how it responds to the warmth of a star for what could be the very first time in its long existence. Perhaps the most significant difference for scientists is when and how we found them. Oumuamua was discovered only after it had already whipped past the sun and was speeding away from us. This gave us a frustratingly short window of just a few weeks to study it, leaving many questions unanswered forever. Borisov was a major improvement. It was spotted on its way in, giving the world's observatories several months to prepare and execute detailed studies as it made its closest approach. 3I Atlas represents the ultimate observational scenario. Its potential discovery so far out in the solar system, years before its closest approach to the sun, is a game changer. This would provide a long, unhurried timeline to watch the entire process of a giant interstellar comet waking up. We could witness the first faint whispers of activity as it warms, tracking its evolution from a dormant, frozen relic into a brilliant, active comet, a spectacle never before witnessed for an object from another star. This extended observational window allows us to probe what we might call the pristine factor. Comet Borisov was considered remarkably untouched, likely on its very first journey into the inner regions of any star system. Its composition seemed to confirm it was a fresh sample from the cold outer edge of its home. Oumuamua's history is more ambiguous. Its dark, reddish surface suggested long-term exposure to cosmic rays, but whether it was a pristine fragment or the remnant of a shattered larger body is unknown. 3I Atlas, as a massive Oort cloud object from another star, would be the definition of pristine. Its enormous size means that even if its surface is weathered by millennia of interstellar travel, its deep interior would remain perfectly preserved, a frozen time capsule from the birth of its solar system. As the sun's heat peeled back its outer layers, we would gain access to materials that have been in a deep freeze for billions of years, untouched by any star. A key piece of the puzzle for any interstellar object is tracing its path back to a potential home. For Oumuamua, this has proven impossible. While it came from the general direction of the star Vega, it wasn't near Vega when it started its journey, and its trajectory doesn't line up with any known nearby stars. Borisov's path was traced back toward a binary star system called Kruger 60, but a definitive link couldn't be established. With 3I Atlas, the long observation arc would allow for an exceptionally precise calculation of its incoming trajectory. Astronomers would meticulously cross-reference this path with star maps showing the past positions of millions of stars. Finding a conclusive stellar origin, a home address, would be a monumental breakthrough. For the first time, we could directly compare the chemical makeup of a comet with the known properties of its parent star, creating a tangible link between a stellar system and one of its wandering children. Each interstellar visitor has left a different scientific legacy. Oumuamua's legacy is one of profound mystery. It challenged our definitions and forced us to consider possibilities we hadn't imagined, from its strange shape to its unexplained acceleration. It was a cosmic question mark. Borisov's legacy is one of confirmation. It showed us that objects closely resembling the comets in our own solar system do indeed exist around other stars, and that we have the capability to study them. It was a reassuring answer. The potential legacy of 3I/Atlas would be one of revelation. It would move our understanding beyond questions and answers into the realm of deep, detailed knowledge. It would not be a single data point, but a flowing stream of information, providing enough data to write an entire chapter on the chemistry and dynamics of another solar system, transforming a field of study from speculative to observational. We can also compare their physical resilience. Oumuamua, whatever it was, remained a single object throughout its passage. It held itself together against the sun's tidal forces. Comet Borisov, however, gave us a glimpse of cometary fragility. In early 2020, astronomers observed its nucleus split, casting off a large fragment as it moved away from the sun. This kind of breakup is common for our own comets and offered valuable insight into Borisov's structural integrity. For the massive 3I Atlas, its reaction to the sun's warmth would be a subject of intense focus. If it is a solid, well-compacted body, it might hold together. But if it is a loosely bound rubble pile, the thermal stresses of its first-ever solar encounter could trigger a cascade of spectacular fragmentation events. Witnessing a giant interstellar comet break apart would be a scientific goldmine, creating a whole new stream of smaller interstellar objects to study in real time. The arrival of these three distinct visitors has fundamentally reshaped our view of the cosmos. Before Oumuamua, an interstellar object was a purely theoretical concept, thought to be an exceptionally rare, perhaps once-in-a-century discovery. Then, just 2 years later, Borisov arrived. Now, the potential confirmation of a third, and such a spectacular one as 3I Atlas, suggests these encounters are far more frequent than we ever imagined. It implies that the space between the stars is not empty, but is instead teeming with these wandering relics of planetary formation. The galaxy, it seems, is a place of constant exchange, with the building blocks of solar systems being shared across vast cosmic distances. This realization transforms our solar system from an isolated island into a port of call on a vast, unseen galactic ocean. It makes you wonder what feelings or thoughts arise for you when you imagine these silent travelers passing through our cosmic neighborhood after journeys of millions of years. The discovery of objects like 3I/Atlas has breathed new life into an old and profound hypothesis known as panspermia. This is the idea that the basic building blocks of life, or perhaps even hardy microorganisms themselves, can travel between star systems, hitching a ride on comets and asteroids. An interstellar comet, rich in water ice and complex organic compounds, acts as a perfect cosmic lifeboat. Shielded from the harsh radiation of deep space within its icy core, these precious molecules could travel for millions of years before being delivered to a newly forming planet. The existence of 3I Atlas and its relatives proves that this delivery mechanism is not just theoretical, it is actively happening. Billions of such objects are likely careening through the galaxy right now. While we have yet to find direct evidence of life on an interstellar visitor, their composition confirms they are carrying the fundamental ingredients, suggesting that the seeds of life might not be unique to our solar system, but are instead scattered widely across the cosmic winds. Have you ever looked up at the stars and wondered about the connections between worlds? It's a peaceful thought to hold as you drift off. And the possibility of confirming such profound connections is about to increase exponentially, thanks to facilities like the Vera C. Rubin Observatory. This next-generation telescope, with its enormous mirror and incredibly wide field of view, is designed to survey the entire visible night sky every few nights. Its sensitivity is so immense that it is expected to find not just 1 or 2 interstellar objects per year, but potentially dozens. Instead of being rare, startling surprises, interstellar visitors will become a regular part of astronomical observation. This will allow us to build a true catalog, comparing their sizes, shapes, and compositions. We will finally have a large enough sample size to understand how common they are, where they come from, and whether objects like the rocky Oumuamua or the cometary Borisov and Atlas are the norm. The observatory will essentially cast a vast, fine-meshed net across our cosmic neighborhood, waiting to see what drifts in from the great beyond. But spotting these fleeting visitors is only the first step. The true challenge is reaching them before they vanish back into the void. The brief window we had with Oumuamua and Borisov highlighted a critical need for rapid response missions. Unlike missions to our own asteroids or planets, which can be planned years in advance, an interstellar object gives us only months of warning. Because of this, space agencies like NASA and the European Space Agency are exploring concepts for spacecraft that are essentially kept on call. These probes would be pre-built and perhaps even pre-fueled, waiting in a state of high readiness for the discovery of a suitable target. Once a promising interstellar object is identified and its trajectory is precisely calculated, this interceptor could be launched within weeks using powerful rockets and clever gravity assist maneuvers to catch up to the visitor for a close-up flyby, giving us our first ever direct glimpse of matter from another star system. This very challenge has given rise to ambitious and tangible mission concepts, one of the most compelling being Project Lyra. Developed by the Initiative for Interstellar Studies, this is not just a vague idea, but a detailed feasibility study on how we could actually send a probe to an interstellar object. The mission architecture is flexible, depending on the target's trajectory. For some scenarios, a powerful rocket like the Space Launch System could send a probe on a direct path. For others, a daring maneuver called a Jupiter-Oberth maneuver would be used, where the spacecraft dives deep into Jupiter's gravity well and fires its engines at the point of closest approach to get a colossal speed boost. Another fascinating option involves using advanced solar sail technology, where a vast, ultra-thin sail would use the pressure of sunlight itself to accelerate the probe over time, allowing it to eventually match the speed of an interstellar traveler. Project Lyra demonstrates that intercepting a piece of another solar system is no longer science fiction, but a genuine engineering problem we are actively working to solve. While we plan missions to catch future visitors, some scientists believe pieces of ancient interstellar travelers may already be here, trapped within our own solar system. Over its 4.5 billion-year history, our solar system has acted like a giant gravitational net, or a cosmic dustbin, sweeping up countless objects that wandered in from interstellar space. Some of these captured objects could have been nudged into stable, long-term orbits within the Oort cloud, the vast spherical shell of icy bodies that surrounds our Sun at an immense distance. In this scenario, some of the comets we currently think of as our own might actually be naturalized immigrants from other star systems, their alien origins masked by their long residency. Finding them would be incredibly difficult, but the tantalizing possibility remains that pristine samples of other stars' planetary systems are not just flying by, but are already part of our celestial family, waiting to be identified. Whether we find these ancient remnants or intercept a new arrival, the key to unlocking their origins lies in reading their unique chemical signature, specifically their isotopic fingerprint. Isotopes are versions of elements with different numbers of neutrons. The ratio of certain isotopes, for example, nitrogen-14 to nitrogen-15, or deuterium to hydrogen, can vary from one star system to another based on the specific conditions in the stellar nebula where they formed. Our solar system has a very particular set of isotopic ratios.
If a comet like 3I Atlas were to be analyzed up close and found to have wildly different ratios, it would be definitive proof of its extrasolar origin. This fingerprint could tell us about the type of star it came from, the temperature of its home protoplanetary disk, and the chemical evolution of a solar system completely different from ours. It's like cosmic genealogy, tracing a comet's family tree back to a distant and unknown stellar hearth. These chemical fingerprints are not the only clues we now look for. Astronomers are actively hunting for a specific type of strange behavior that first mystified us with Oumuamua: non-gravitational acceleration. This is when an object's movement deviates slightly from the path dictated purely by the sun's gravity. For a normal comet, this is easily explained by outgassing, as sublimating ice acts like a gentle rocket engine. But Oumuamua showed this acceleration without any visible coma or tail. This led to much speculation. For future surveys, this very phenomenon has become a key flag. If an object is moving on a hyperbolic path and shows a tiny, unexplainable push that isn't accompanied by visible outgassing, it will be immediately prioritized for intense observation. This strange behavior could indicate a composition unlike any comet we know, or perhaps a physical process we don't yet understand, making it a prime candidate for a truly alien artifact. Searching for such subtle deviations in motion across millions of celestial objects every single night is a task far beyond human capability. This is where artificial intelligence and machine learning are becoming indispensable tools in the search for interstellar visitors. The data firehose from the Vera C. Rubin Observatory will produce more information in a single night than astronomers have been able to process in decades. Sophisticated algorithms are being developed to sift through this data in real time. These AI systems will be trained to recognize the telltale signature of a hyperbolic trajectory, the unique light curve of a strangely shaped object, or the subtle signature of non-gravitational acceleration. The AI can automatically flag candidates, trigger follow-up observations from other telescopes around the world, and calculate potential intercept trajectories, all within hours of initial detection. The discovery of the next interstellar object will almost certainly not be made by a human eye looking through a telescope, but by a silent, intelligent algorithm scanning the digital cosmos. As our technology gets better at finding these objects, each new discovery adds to a grander narrative, one that suggests the very ingredients for worlds like ours are shared across the galaxy. The confirmation that interstellar comets carry abundant water ice is particularly profound. It supports the theory that Earth's oceans were delivered, at least in part, by cometary impacts early in its history. The discovery of interstellar comets implies that this same process, the delivery of water via icy couriers, could be happening in countless other fledgling solar systems. It paints a picture of a galaxy where the potential for habitable, water-rich planets isn't a fluke confined to our own backyard. Instead, it suggests that the fundamental components for life-bearing worlds are constantly being exchanged between stars, making the prospect of finding another Earth-like planet somewhere out there in the vast darkness all the more likely. This sharing of water, of organic molecules, and of planetary building blocks leads to the ultimate legacy of comets like 3I Atlas and the interstellar objects that came before it. They have fundamentally and irrevocably shattered the idea of our solar system as an isolated island. We now see it for what it is, an open harbor on the shore of the galactic ocean, with travelers from distant ports arriving constantly.
These objects are tangible proof that pieces of other worlds are not just a theoretical concept, but are physically within our reach. They are emissaries from other stars, carrying clues about their birth, their journey, and the nature of solar systems we may never see directly. They remind us that the space between stars is not empty, but is a dynamic environment filled with the wandering ghosts of planetary formation. And they offer the humbling yet thrilling realization that we are deeply connected to the rest of the cosmos. Thank you for listening to these calming facts tonight. If you'd like to continue exploring the quiet wonders of our universe, please subscribe and join us again for more sleep-friendly science to help you relax and drift away.